This is the last part of my guest lectures on electron spin, in which I'll focus on normally non-magnetic systems which are pushed out of spin-degenerate equilibrium by spin injection from an external ferromagnetic source. I'm going to first tell you why we want to study these systems, and why this is such a hard problem, or at least why the most straightforward approach to solving it is bound to fail. Then I'll show you one particular way that I have personally used to obtain spin injection in silicon and germanium semiconductor devices, and a little bit about what can be learned as a result. To motivate the kinds of information about non-equilibrium spin transport we're after, I want to appeal to the history of non-equilibrium charge transport, namely minority carriers in semiconductors. The seminal measurements were done by Haynes and Shockley in the mid-20th century at Bell Labs. In these time domain experiments, a narrow pulse of minority electrons were injected into p-type semiconductors filled with equilibrium holes. An electric field carried these electrons to a charge detector where the pulse could be analyzed. By measuring the time of flight, they could determine the minority carrier mobility, or the proportionality constant between applied electric field and electron velocity. By measuring the spreading of the pulse in time, they determined the strength of random thermal fluctuations from scattering, the minority carrier diffusion coefficient. And by integrating over the pulse and determining how many electrons made it without annihilating with a positively charged hole, the minority carrier lifetime could be determined. Without these values, none of the solid-state devices we use today could be designed and successfully made. So, if we speculate any use for spin-polarized electrons out of equilibrium in semiconductor devices, then we at least need to be able to measure the spin analogs of these parameters. So let's first look at why it's not so easy to transfer the substantial spin imbalance, spin polarization, from a ferromagnet into a non-magnetic electronic material, especially when using a semiconductor in an effort to make, for example, new kinds of spin transistors. The most straightforward way one might naively try is to make an ohmic or linearly resistive contact between the ferromagnet and a semiconductor. Let's see how this works for plain old charge injection. Ohm's law says that the charge current density flowing is proportional to the conductivity and driven by a spatial gradient of an electrochemical potential. This combines the effects of electric field, gradient of electrostatic potential, with flow from high concentration to low via random thermal fluctuations comprising the random walks of diffusion. If we incorporate the device geometry, we can use this expression to recover the more familiar V equals IR form of Ohm's law. In metal semiconductor ohmic contacts, current is conserved across the interface, but the conductivity in the metal is large, so the potential energy provided by a voltage Q times V drops mostly across the lower conductivity semiconductor. Now, if we want spin injection to accompany this charge injection, then the currents for spin up and down must be different, since the conductivities for up and down are the same in the semiconductor. Their respective electrochemical gradients must be different. This is what we need to happen on the semiconductor side. Spin up and down electrochemical potentials have different gradients to drive asymmetric current densities comprising a spin current. The one avoidable consequence of this asymmetry is an electrochemical splitting at the ohmic interface. Using Ohm's law, we can obtain a relationship between current polarization and this electrochemical potential splitting. The first term in parenthesis is due to the average potential drop over the transport length scale L. Note that although J up and J down are not equal, their sum does equal the total charge current as expected. Now we have to derive equivalent expressions on the ferromagnet side, where we will see the deleterious effect of the splitting on spin injection. On the ferromagnet side, the electrochemical potential splitting relaxes to zero in equilibrium due to spin flips away from the interface. The spin relaxation length scale is the so-called spin diffusion length, lambda. By once again applying Ohm's law, we get the following expressions for the current densities of spin up and down on the ferromagnet side. Note that there are two important differences between these expressions for the ferromagnet and the ones above describing transport in the semiconductor. First, the spin-dependent conductivities are not equal in the ferromagnet due to their dependence on the asymmetric carrier densities. Second, and as a result, the deviation of the interface electrochemical potentials from equilibrium are not symmetric. In other words, C up is not equal to C down in this figure. However, because the ideal interface preserves spin, the electrochemical potentials are continuous, so we do have the sum rule giving us a total splitting, which we need to determine the spin polarization flowing across the interface in the semiconductor. Using the definitions of both the injected current polarization and the bulk ferromagnetic polarization, we can derive a simple expression for the splitting on the ferromagnet side. In intimate ohmic contact, the electrochemical potentials are continuous, so this is the same as a splitting on the semiconductor side. We can therefore substitute it into our previously derived expression to obtain this result. Note that this is very different from our naive expectation, since it depends strongly on the magnitude of a dimensionless parameter epsilon, the ratio of conductivities and transport lengths across the interface. If epsilon is much less than 1, then only when the bulk magnetic polarization, beta, is approximately 1, a half metallic ferromagnet, do we recover the desired case where the injected current polarization P is approximately equal to the bulk ferromagnetic polarization beta. Unfortunately, the bulk polarization of typical ferromagnets is around 50%, so as this plot shows, ohmic injection is doomed unless epsilon is at least 0.01. However, the relevant materials properties are not forgiving in this respect. The ratio of conductivities between a semiconductor and a ferromagnetic metal is significantly below unity, even for highly doped semiconductors and highly disordered amorphous ferromagnetic metals. Likewise, the ratio of length scales is small due to the fast spin relaxation in the ferromagnet, leading to spin diffusion length, lambda, of approximately 10 nanometers, whereas in semiconductors with low spin orbit interaction, such as silicon, transport lengths can be 10 microns or longer, even at elevated ambient temperatures. Therefore, even in the best scenario, epsilon is approximately 10 to the minus 4, leading to the negligible polarization shown in the figure. Over the range of expected values for epsilon, one needs bulk polarization of at least 95% for injected polarization of greater than 10% or so. So elemental ferromagnets, iron, cobalt, and nickel, are useless for spin injection in the ohmic regime. In fact, the problem is evident even graphically. The splitting delta mu, which is necessary for a non-zero injected current polarization, also tends to reverse the spin-up electrochemical potential gradient at the interface on the ferromagnet side, inhibiting injection of the very spin species we want to inject into the semiconductor. Therefore, in order to maintain the constraint of current conservation across the interface, the steady-state interfacial splitting is small, and the injected current polarization P is negligible. Modern techniques to overcome this problem include quantum mechanical tunneling and, in my lab, ballistic hot electron injection, which circumvents the issues relevant for ohmic injection here. I'm not going to describe the details of spin injection and detection. That's a whole other course in device physics and magnetism, but rather what we can learn from measurements of spin transport and manipulation by any means. The key to extracting the most information from these measurements is exploiting a topic I mentioned several segments ago, spin precession. Again, this is the magnetic analog of a spinning top or gyroscope with an off-axis gravitational force causing a mechanical torque. In spin transport devices, we apply a magnetic field perpendicular to the injected spin direction but parallel to the transport direction caused by electric fields, and the spin will precess in a plane. The final spin precession angle is determined by the product of spin precession frequency, determined by magnetic field strength, about 28 gigahertz per Tesla in a material with weak spin orbit coupling like silicon, and the transit time, inversely proportional to electric field strength. If we apply a perpendicular magnetic field with the appropriate strength, then you can cause the spins to precess an average of 180 degrees, fully flipping with respect to their injected polarization. Your experimental measurement of sigma z, the spin along the initialization axis, will then vary. Doubling the magnetic field doubles the precession frequency and therefore results in an average precession angle of 360 degrees, a coherent full rotation restoring the expectation value of sigma z. As you can see from this actual experimental data, it doesn't matter whether the field polarity is positive or negative. In other words, it doesn't matter if the spin precesses clockwise or counterclockwise. Now, if all electrons had the same transit time from injector to detector, we would expect this cosine-like oscillation to continue indefinitely for higher and higher orders of precession rotations. But that's not what happens. In reality, not all electrons have the same transit time due to random scattering processes. Therefore, an uncertainty in transit time gives rise to an uncertainty in precession angle. When the precession frequency grows and higher magnetic field, the effects of partial cancellation can be seen and the oscillations diminish. We can model this measurement with a transport simulation, summing up the cosine-like contributions from electrons with a distribution of arrival times in order to fit the non-equilibrium spin mobility and diffusion coefficients we're after. However, there's a model-independent method with far greater utility. The key is to recognize that this integral summation is really just the Fourier transform. Therefore, the oscillations we measure can be inverted to yield the empirical transport distribution without any model dependence whatsoever. In this example, we can see the effects of increasing the electric field. Oscillation period increases, and the number of oscillations themselves grows, but the transforms clearly show that this is a result of smaller mean transit time and standard deviation. This method of obtaining time of flight is called the Larmor clock. We don't make an explicit measurement of transit time. We measure the angle of rotation at a known angular velocity, the same way we measure time from an analog clock. We know the rotation speed of the hand for the clock, 360 degrees per hour for the minute hand, and infer time from the instantaneous orientation. We're likewise measuring the spin orientation and determining how long it precessed in a known magnetic field. For measurements of spin transport, we can correlate the transit time with final spin polarization and extract the spin lifetime. In silicon, we can see that although the non-equilibrium lifetimes of hundreds of nanoseconds are fairly long in comparison to the momentum relaxation time of picoseconds or less, they're strongly dependent on temperature, increasing dramatically as a sample is cooled. This demonstrates the importance of relaxation via a nominally spin-independent process, electron scattering off of thermal phonons, distortions in the crystal lattice. This electron-phonon spin relaxation process results from the fact that due to the weak but non-zero spin-orbit coupling, the electron wave functions are not pure spin eigenstates up and down. Rather, spin up has a small amount of spin down and vice versa, but remain fully orthogonal. We can calculate the transition rate between these states constituting a spin flip due to momentum scattering of these free electrons from wave vector k to k prime by using the so-called Fermi-Golden rule. This first-order expression is proportional to the square of the matrix element of the scattering potential coupling the two initial and final states and the density of final states rho. Now, even if the scattering potential only couples states of different momenta k, due to the spin-orbit mixing of the wave function, we see that there is a non-zero matrix element, and this is exactly equal to the quantity determining the spin-preserving momentum relaxation rate. The spin relaxation is therefore proportional to the momentum relaxation and also proportional to the square of the typically small spin mixing amplitude. This being the end of my contribution to this course, I'm obliged to acknowledge support not only for my experimental research on spin transport, but also support for scientific outreach efforts to students and the public outside my institution, the University of Maryland. In particular, the National Science Foundation Career Award has made this work possible. It's been my great pleasure to share this quick story of electron spin with you, and I invite you to learn more about spin through your own study, and perhaps even original research in physics and engineering labs around the world.